So today we are going to start our discussion on algorithms for solving constraint optimization problem. So reminding you, our goal from today onwards is to study algorithms that can solve problems of this type. We'll introduce 4 different algorithms. First is barrier method, which we are going to study today. Then we'll do augmented Lagrangian. Then the third one is sequential quadratic programming. And the fourth method is Lagrangian method. So these are the 4 methods that we will talk about. So today, so there is midterm on Wednesday. So I haven't announced anything about midterm, but this is a formal announcement that we have midterm on Wednesday. And you will be allowed 1 page of cheat sheet, both sides. So you can write whatever the heck you want to write on that cheat sheet, and you can write it in as small of a font as you want. And you can get it to the class for your midterm. The midterm will be in class during the 12:40 to 1:35 time slot. I am able to complete the midterm in 7 minutes. You get 55 minutes to complete the midterm. So I hope that is reasonable and fair. You can refer to your cheat sheet in order to write your answers. No electronic gadgets, no cheat sheet on your iPad, no cheat sheet, no books allowed in the classroom. So, and no calculators will not be needed. Okay, so I'm not making a midterm so that you need calculators. So you don't need to use calculators at all. So that's roughly it, the description about the midterm. Any questions on the midterm? Yes.
What is the latest topic covered?
Oh, assignment 1 to 3.
1 to 3. So no
Lagrangian method, no. All of this is part of midterm too, so you're not off the hook for this stuff. But the second midterm is November 11th or 15th or something like that. So we'll talk about dynamic programming, and we'll talk about all the Lagrangian stuff in that particular midterm.
Same class time.
Same?
Same class time, right?
Same class time, yeah, class time. And you will have 2 cheat sheets in that. So 1 cheat sheet from midterm 1 and then another one from midterm 2.
So another problem is still about the midterm scope. So for the practice midterm, as problem 4 is the Lagrange multiplier.
Right.
So are we going to have this count?
That was previous midterm. That is ECE 5759.
So
that was long time ago.
So this one is not included in our midterm.
So in that particular course, the schedule was different. In this course, the schedule is different. So yeah.
So that'll be the lecture 1 to lecture 14.
Not 14 specifically, but I think optimization over convex sets.
Okay.
So right now we are talking about Lagrange multiplier method, but optimization over convex set is the end of the thing.
Another problem is that as I go to review the previous quiz 1 and quiz 2, the questions got mutated. So please.
Oh yes, somebody did mention to me that I'm supposed to, make it public. So I should be doing it today. I'll try to do it right after the class. But if I've not done it by end of day today, please do send me an email and I'll do it right away. Okay. I'm so sorry for not doing it. I was supposed to do it over the weekend, but I didn't get a chance. Any other question? Yes.
How many questions are there?
4. Yeah. But each question has subparts. Okay. Any other question? Awesome. You know, the good thing is you guys didn't ask me what are the questions on the midterm, but I've had that conversation with someone before, like what questions are coming in midterms. So you guys are a bit, you know what questions to ask, which is a good skill to have. Okay. Okay. So moving forward, these are the 4 methods we are going to study over this week and the next week. There's no class on Friday because it's fall break. And then after we complete these things, we'll move on to dynamic optimization. So then we'll use all the methodology that we have developed so far in order to solve dynamic optimization problems. Typically speaking, long time ago, we used to spend more time on static optimization and less time on dynamic optimization. But we've changed the syllabus a couple of years back, and now we spend half of the semester on static optimization and another half on dynamic optimization. Okay. All right, so let's move on to barrier method. In each of these algorithms, we start with a very different set of constraints. Like by specifying the constraints, we come up with, we have designed different algorithms. So for barrier method, we are only going to look at inequality constraints of this type. But let me introduce what class of problems barrier method solves. And then we'll of course talk about many of these methods later on. Okay, so the problem is I want to minimize f of x. X is in capital X such that g of x is less than equal to 0. X is closed. So X is a closed set here. And naturally, f and g are continuously differentiable functions. Okay, but it's not an arbitrary closed set. This closed set and constraint must satisfy a very specific condition. So let's try and introduce what that condition is. Let me introduce the set S as x in capital X such that g of x is strictly less than, or gj of x is strictly less than 0 for all j equals to 1 to r. And the class of x g pair must satisfy for every x in capital X gx less than equal to 0, there exists a sequence xn in S such that xn converges to x. So for barrier method to work, we need to make this particular assumption. Okay, so after you note it down, I'm going to unpack what this assumption means. What does this requirement imply? Okay. So look at the original problem. The original problem is I want to minimize over a set, closed set. So this has to be a closed set. I want to minimize this function such that g of x less than equal to 0. So at this generality, if we are just looking at this particular problem statement, I could have a bunch of points and at all these points, this is my set capital X, just these points. It's a closed set because it's a bunch of points. And let's assume that g of x is less than equal to 0. So g of x is this line, g of x equals to 0. This is g of x less than 0. This is g of x greater than 0. And this line is g of x equals to 0. So all these points satisfy g of x less than 0. So all the points are in the constraint set. X is a closed set. But then I can't really do any gradient descent because there's no point through which I can approach each of these different points in the space. So that's why we need to make this assumption wherein for every x in x such that g of x is less than equal to 0, there exists a point in the interior of the set. So this is an interior of the set. So this is x in capital X such that gj of x is less than 0. So this is strict inequality. So I can come up with a point xn in this particular set such that xn converges to the point x that is given here, that satisfies these two qualities, which is x belongs to the closed set and g of x is less than equal to 0. Oh, actually, maybe I need to have a point here on the set also for this thing to work. Yeah, so these are the points where g of x is equal to 0, but I can't approach this point from inside the set.
Xn sequence or just a point?
Xn is a sequence. So this is a notation for a sequence. So n goes from 1 to infinity.
Does that mean that there are no holes in the set or something?
Yes, exactly. So, but it's not just about holes, it's about being able to reach the boundary from interior of the set. So let's say I want to reach the corner of this room, okay? And so in this particular room, of course, it's a convex set, so I can reach the corner by just being in the interior of the set. But you could imagine a hypothetical situation where there is like an isolated point at the boundary, but you can't reach that isolated point by just going through the set, going from the interior of the set. It'll become clear why we need to make this assumption once I introduce the algorithm, but this is the assumption that is needed. So for instance, if I have a set that looks like this, and then these 3 points at the boundary, I can't reach the boundary from the interior of the set. Okay, so then I cannot use barrier method in these cases. Okay. Of course, there are many methods like that in optimization. We are only studying 4 methods in the class, so we're not going to cover all the different methods that are needed to solve important problems. But it's just an introduction to optimization anyway. So wonderful. So we are going to avoid this condition. And what is the algorithm? Let's look at the algorithm. Well, let me give you an example of a set that we are going to study very soon. So my x is in Rn, Ax equals to b, and my g of x is equal to minus x. So the problem statement is I want to minimize f of x such that Ax equals to b, x is greater than equal to 0. So this is my closed set, closed convex set, and g of x is negative of x less than equal to 0, which is the same as x greater than equal to 0. Okay, so we are going to solve problems of this type by using the barrier method. Specifically, if x is convex and g is convex, so of course x is a convex set and g is a convex function, then this condition is satisfied. So whatever condition I have written here, if you are looking at a convex set and a convex constraint, then the condition is automatically satisfied. So we don't have to apply our brain and try to see whether this condition is met or not met.
Is it a sufficient condition?
It's a sufficient condition, yeah. So to give you an example of a non-convex set, let's say You are optimizing something over a donut. I don't know what you would be optimizing, but let's say you have a donut and you're optimizing over that space. It's a non-convex set, but it would satisfy this particular condition. So you could have non-convex problems that satisfy this condition, but so what would be the constraint like? So I want to minimize f of x such that norm of x is less than equal to R2, R1 less than equal to x less than equal to R2. So that could be optimization over an annulus, which is a non-convex set. But you can reach the boundary from the interior of the set, right? So
is that set X or S?
So this interior is the set S. This is the set S, but if you include the boundary, it becomes X. Well, not just X, but X such that G of X is less than equal to 0. The boundary is X such that G of X equals to 0. Interior is Gx is strictly less than 0. Okay, any questions so far? Okay, so what's the idea in the barrier method? The barrier method says, let's assume that the point, it doesn't matter if the optimal point is in the interior of the set or the boundary of the set. I'm going to create a function that's going to optimize in the interior of the set so that even if the solution is at the boundary, I can approach the point from the interior of the set. So to give you an example in this particular set, let's say this is my x star. I start with some point x naught and I'm going to be in the interior of the set and I'm going to try to reach x star by going through the interior of the set itself. And the way to solve, the way they come up with this algorithm is they create a barrier function around the boundaries, and then they try to solve the problem where you add the objective function with the barrier and you optimize over the set X. So what's the method like? I create xk equals to argmin x in capital X f of x plus epsilon k b of x. Epsilon k goes to 0. B of x is known as the barrier function. And there are various choices of barrier function. B of x equals to minus summation j equals to 1 to r log minus gj of x. This is called logarithmic barrier function. And then we have inverse barrier. Okay, so here is the setting. I have a function. This is my f of x. I'm trying to minimize it over A less than equal to X less than equal to B. I'm going to create a barrier function B of X which goes to infinity at the boundary. So as Gj of X goes to 0, remember Gj of X is less than equal to 0. Okay, so minus Gj of X is a positive number, and as this term positive number goes to 0, what is log of 0? Not infinity, minus infinity. I'm going to multiply it by a negative sign, it becomes plus infinity. So as this term goes to 0, this barrier function goes to infinity. Yes.
Should there also be a summation from 1 to R?
Oh yeah, there, this one, right? Yeah. Perfect, thank you. So there is a summation here as well. So the barrier functions are created so that as I'm approaching the boundary, so I'm here, my barrier function is some finite value, but as I'm approaching the boundary of the set, the barrier function goes all the way to infinity. So this term is going to infinity, but this term is going to 0. Okay. So eventually what happens is you reduce the value of epsilon k in a manner that the barrier becomes less and less useful, and then you are trying to minimize the function f of x over the constraint set in an appropriate fashion. But you're still not going to violate the constraint of gx less than equal to 0, because your barrier function is taking care of the fact that even if this is 10 raised to minus 5, if this becomes 10 raised to 20, you're still trying to make sure that you are within the constraint region. So essentially this is f of x. This is your f of x plus epsilon k b of x. So going to infinity at a, going to infinity at b, but is taking a finite value in between that constraint. Okay, and one of the main results in the book is if you're solving this problem at every point of time, xk converges to x star as k goes to infinity, because you're taking epsilon k going to 0. We won't cover the proof, as I said. I only want to cover necessary and sufficient conditions, but not cover some of these proofs within the class. But the proof is there in the book, so feel free to.
xk decreases faster than b of x.
So xk, you mean xk?
I'm sorry.
No, f of xk.
No, epsilon k.
Epsilon k. So epsilon k has to go to 0, but remember that b of x is still infinity at the boundary. Okay.
But the combined term epsilon k b of x goes to 0.
Well, the point is how quickly you are going to infinity. So if epsilon k is very, very small, then within the constraint you are not going to see much. Sorry, in the interior you are not going to see much. But let's say your epsilon k was extremely small. Epsilon k is 10 raised to minus 10. Then in that case, this is your f of a, right? So then it will look very similar in the rest of the place, but here it will start going to infinity. And same thing here. Here it will start going to infinity because your epsilon is very small, right? So b of x is negligible in the interior, but it becomes extremely large very close to the boundary. So you can think of it as very sharp corner. So when epsilon k is small, if it's equal to 1 or 2, then you have very smooth corner, so it just grows to infinity somewhat slowly. But when epsilon k is extremely small, then it goes to infinity very quickly at the boundary. Yes?
Are we able to converge to an optimal point on the boundary?
Yes, you are able to converge to the optimal point at the boundary as k goes to infinity. Remember, we never run the algorithm until k goes to infinity. So you will eventually end up with a solution that is in the interior of the set. You will never reach the boundary, but you're close to the optimal anyways, so it doesn't matter. Right? All you want is a theoretical proof that as k goes to infinity, you are at the optimal solution. So if you stop your iterations at k equals to 20, I mean 20 is not infinity, it's far away from infinity, but still you are close to the optimal solution. And I think by now you have created enough plots in your assignments to know when you are close to the optimal and when you are not close to the optimal. You look at this first derivative of the function norm, or you look at the error ratio, and you try to see if the error is going to 0 or not. Any other question? Yes.
So this is a method to basically, other than the capital X set, we are turning the constraint problem into unconstrained optimization.
Not quite unconstrained, but remember, typically here this X is going to be a convex set. So you are converting a problem with inequality constraint to a problem of optimization over convex sets.
Because that set didn't correspond to like a convex set.
It may not. It may be a complicated function, right? So remember the problem statement that I had written. I want to minimize f of x such that norm of x is less than equal to R2, right? So this is a complicated function. I don't know how to solve this problem, but I know how to solve unconstrained optimization, and I know how to solve optimization over convex sets. Those are the two algorithms I know. Now, I gave you this problem, and you need to be able to map it to a problem that you already know how to solve, for which you already have a code written. So this is the barrier method, is a way to convert it to a problem that you already know how to solve. Okay. Remember, optimization over convex set is also an infinite iteration problem. So you have an outer loop where you are changing epsilon k, and you have an inner loop where you are solving the optimization problem over the convex set in order to solve the optimization problem. So that's, in theory, you are running two infinite loops. One is the outer loop, and then one is the inner loop. In practice, you're running the outer loop for 20 steps, and you are running the inner loop for 5 steps per iteration. So in 100 steps, you get close to the optimal solution.
Question.
Yeah.
So when we have that problem, so the constraint is not convex set, and the feasibility set is not convex, probability set is not convex.
Right.
And when we turn, like, using barrier methods, when we have a solution, do we know that that is probable optimum?
You only know, so there is a theory and there is a practice. In theory, if you are computing argmin at every point of time, you are getting to the optimal solution. In practice, you're never computing argmin, you're computing a stationary point. So all you are converging to is a stationary point in the limit. But stationary point is not optimal, as we have all understood by solving a lot of optimization problems. Okay. Any other question? Now, of course, in the case of convex function, convex barrier function, convex everything, convex set, then you know that stationary point is optimal because sufficient condition is also necessary. So then you are guaranteed to converge to the optimal solution. Yes?
Can we say that when k goes to infinity, the cost function, modified function is just the original function with the barriers?
That's right. That's right. Yeah. Okay. So let's look at an example.
One more question.
Yes, yes,
sometimes
please.
it is not easy to randomly generate the points inside a feasible set.
Yes, absolutely.
So is there also like a method for that too?
Not quite. How to generate a point within the feasible set is an art in itself, and we are not going to cover that art in the entire course. Okay. Generally speaking, as a practitioner, if you are solving a problem again and again, then you would know what a good initial condition should be. So if you're driving a vehicle, then you know a good initial condition is velocity equals to 0, and maintaining all the constraints. Like if it is red light, then my velocity is 0. If it is green light, my velocity is something. But so you have some idea about that particular problem statement to be able to pick a good initial condition. But frankly, if you're given just a problem out of the hat, it's extremely difficult to know what a good initial condition should be. What is an x naught that lies in capital X? Good question. Anything else? Okay. I want to minimize half of x1 square plus x2 square such that x2 is less than equal to 2. Or rather, x2 is greater than equal to 2. What is the optimal solution here? What is x star?
X2 is 2.
0, 2. Right? I can pick x1 equals to 0, x2 equals to 2. Satisfies the constraint, is the minimum value. What is my capital X here? What is this closed set, capital X? Rn, R2. What is my g of x?
2 minus.
Okay. Let's pick the log barrier function. So what is my b of x? What is my b of x? Minus log minus barrier minus constraint. So minus log. I have only one constraint, so there is no summation. Minus 2 minus x2 equals to minus log x2 minus 2. So what is my f of x plus epsilon b of x? It's half x1 square plus half x2 square minus epsilon log x2 minus 2. How do I solve this problem? Minus, I want to minimize what is x star. Let me call it x epsilon star. Arg min x is in R2, ff(x) plus epsilon v of x. Is it easy to solve? Can someone check if this problem is easy to solve or not? So this is an unconstrained optimization problem, right? So I started with a constrained optimization. Now I'm left with an unconstrained optimization over R2. I have to do argmin, but I don't know if I can solve this problem easily or
That's convex.
not just convex, it's unconstrained. This is unconstrained. Oh, but yeah, this objective function is also convex. Yeah. The objective function is also convex. So one of the things that I did not say, but is true, if each of these GJs is convex, then the barrier function is also convex. This is an assignment problem, so you will definitely see it for yourself. That is indeed the case.
But if that was not convex, that would not convex,
then it would be then it would be non-convex, but it's still yeah, you will come to a stationary point if you were solving that problem. Okay, can someone do the optimization and tell me what the optimal solution looks like? What is x star epsilon? All we have to do is take the first, so this is a convex problem. So all we have to do is take the first derivative, set it equal to 0. So should I do it, or maybe I can use the wisdom of the crowds? You can all vote on what the optimal solution is, and hopefully the majority is correct. You have X star?
Yeah, the first term should be x1, and the second term is x2 minus 1 over x2 minus x2, so the solution is the same to the 0, 2, because when
For every epsilon greater than 0?
no, when epsilon goes to infinity, because it
No, epsilon goes to 0, right? Yeah, so 0 I know, that's already known. But for a finite epsilon, epsilon greater than 0, what is the solution I get?
it's x1, and the first term is x1, and the second term is epsilon times the rest of the x2 minus 1 over x2 minus x2.
Just tell me what the final solution is.
Okay. So it should be epsilon.
No, I think everybody else will be solving it. So I just want. No, that is the optimal solution with epsilon equals to 0. I'm trying to ask what is x star epsilon is. For a value of epsilon which is greater than 0, what is x star epsilon? If you can solve it now, then you are prepared for midterm. So think of it as pre-midterm. What is the first term here for x star epsilon? So let's differentiate this. The first derivative is x1. Second derivative is x2 minus epsilon over x2 minus 2. This should be equal to 0.
x2 is 1 plus minus square root of 1 plus epsilon.
Sorry, can you say that again?
1 plus minus square root of 1 plus epsilon.
This looks correct? Okay. How many of you think this is the correct answer? How many of you think this is the wrong answer? Sorry? How do you say it's, why do you think it's going to be plus?
Because x2 is greater than equal to
Wonderful, yeah. Because remember, g of x is, this term has to be finite, right? So we can't take the minus 1. Perfect. So how many of you think this is the correct answer? I'm going to do proof by democratic means. So you have to raise your hand if you feel strongly about this issue at hand. 1, okay, 5, 6 people. How many of you think this is the wrong answer?
When epsilon is 0,
Epsilon is not 0. Epsilon is finite number right now. This is x star epsilon. This is not x star 0. Okay.
Also, if it's 0,
Then it's, yeah, exactly. Yeah, but I still need to make sure that everybody agrees with this solution. How many of you want to abstain from voting on this issue? No one. Okay. All right. This is the correct answer. Perfect. This is proof by consensus. Everybody agrees, so therefore this is the right answer. Now, as I let epsilon go to 0, I recover this particular solution. And you will notice that this solution, remember this solution is never at the boundary. For every epsilon greater than 0, this solution is away from the boundary. And in the limit, as epsilon goes to 0, I get to the boundary, which is where the optimal solution lies. Awesome. Okay, so now I want to talk about this central path method for solving linear programming problem. So I want to minimize C transpose X such that AX is equal to B, X is greater than equal to 0. This is a linear program. I want to come up with an algorithm to solve it. And remember, we talked about manifold suboptimization method to solve problems of this type. And there we were talking about 1930s and 1940s. Okay, so now I'm going to move to 1980s. Okay, so this is 1980s. Simplex algorithm / manifold suboptimization method is the widespread method for solving this problem. You are tasked by the university president to come up with a different algorithm to solve this. You learnt about barrier method recently, and you think this method is going to be pretty cool to solve problems of this type. So let's set it up in the barrier methods type framework. So what's my set X? What is B of X? We are using logarithmic barrier function. We could use inverse barrier also. We didn't use the inverse barrier, we used the logarithmic barrier. So right now, let's just focus on logarithmic barrier function. So what is B of X? If you want to use log, so it's negative log negative constraint. Constraint is negative x, so negative log xj. I'm summing up j equals 1 to r. And my x star epsilon is going to be argmin x in capital X, f of x plus epsilon b of x, which is equal to argmin C transpose X minus epsilon summation Let's try to visualize what the problem is. So I have a space Rn, and I have this constraint that x has to be greater than equal to 0. So I have this this hyperplane over which I have to minimize this function C transpose X. right? So everyone can visualize this hyperplane. So this meets the axis at this particular point, and I'm trying to minimize C transpose X. So maybe my optimal solution would lie here. Maybe this is my X star. So one thing that, again, we have not covered in the class, but it's true. If you want to minimize a concave function over a convex set, the solution will always lie at the boundary. So it turns out that linear function is both convex and concave. So let's assume that this is, let's say this is a concave function here. It's a convex set. So the solution will always lie at the boundary. So this is my X star, and I want to solve this, use this barrier method, logarithmic barrier method, to solve this problem. So I'm going to generate a sequence. This is X star of epsilon. And as I go from epsilon from infinity to epsilon equals to 0, I'm going to be tracing a point on this, but tracing a line on this hyperplane or on this manifold, and this is known as a central path. So this is X star epsilon or epsilon 1, this is X star epsilon 2, this is X star epsilon 3, and so on and so forth. So this is known as a central path. This particular curve on this manifold is called the central path. And what this algorithm is trying to do is to trace this central path in order to get to X star. That's what we are trying to do. Okay.
And in each step, we can solve it using like state of example or something.
Right. So now this becomes a problem over over a convex set, Ax equals to B. What we have learned in our previous theory is projecting onto this set is easy. Projecting onto this set is hard. So remember, inequality constraints projection is very difficult. So now what I'm doing is solving a problem where I have an objective function over a set over which it's very easy to project, right? So we'll try to solve problem and over this set, and we'll trace the central path starting from X star epsilon 1. So we pick epsilon 1, I'm going to try to get to this point. Then I'll pick epsilon 2, then I'll try to get to this point, then I'll pick epsilon 3, I'll try to get to this point. And by taking epsilon going to 0, I'm going to get as close to X star as I want. Now this sounds somewhat wasteful. It's wasteful because in order to get here, you need to run infinite number of iterations. Then you pick epsilon 2, then in order to get here, you need to run infinite number of iterations, and so on and so forth. So instead of trying to trace so the algorithm says you need to trace the central path exactly. But we are optimizers. We want to get shortcut to the final solution. So in order to get shortcut to the final solution, if I tell you to walk straight, but instead you are zigzagging around the straight line, you will eventually end up reaching the final destination that you want to reach. So instead of trying to trace the central path exactly, we will actually start somewhere here, and we will try to trace the central path approximately in order to get to the final destination. And in this approach, we are going to save a lot of complexity of the optimization problem, because now we don't have to run infinite number of iterations. So what I'm going to talk about, I hope we have some time. Only 5 minutes? Okay. All right, so I'll give you an overview of what we are going to do next week on Monday. So we'll start with some initial condition. We'll try to get close to the central path. So we need to have a metric of how close we are to the central path. Okay, so step 1 is get a metric on how close we are to central path. The second step would be to take 1 Newton step in the direction of the in order to solve this particular problem. So first we get close to this, then we take 1 Newton step, or rather constrained Newton step, and the third part is figure out a way to reduce epsilon k. And then I go back to this, and then I do this again. So initially I go to step 1, I am standing at some random point in the space, and then I get close to the central path on the manifold. Once I am close to the central path, I'll take 1 constrained Newton step. Okay, I'll get even closer to the central path. After that, I'll reduce my epsilon k. Okay, and then I'll take another Newton step. I'm still close to the central path after 1 Newton step, but with a different epsilon k, with a smaller epsilon k. And then I'll take another constrained Newton step, and then I'll reduce epsilon k again, and I'll keep doing this until I satisfy some convergence criteria. And that would be my algorithm. This is known as an interior point method for solving linear programming problem. It was developed in 1980s with the log barrier function. There were other barrier functions that were studied in late 1970s, but eventually in 1980s somebody said that let's look at the log barrier function, and by solving this particular, by coming up with this approach, the author of the paper showed that you can converge to the optimal solution in minimal number of time steps. Okay, minimal number of computational steps. So that was the big breakthrough at that point of time, because this algorithm had much lower complexity in comparison to manifold suboptimization method. Now that's theory. In practice, manifold suboptimization method seems to work better than interior point method, because whenever you look at the algorithmic complexity, you're looking at the worst case scenario, whereas the kind of problems we are generally exposed to are somewhat, it has a lot more structure to it. You know, we are solving an optimization problem of an autonomous car driving on the road, or we are solving an optimization problem for integrating renewable energy into the grid. So those problems have a lot of structure, as a result of which the manifold suboptimization method works equally well. But this algorithm is known to have extremely low complexity for the worst case problem you would ever encounter in the linear programming in your life. Okay, so anyways, that's the theory. We'll talk more about it next Monday. Good luck with your midterm preparations. And if you have any questions, feel free to reach out to me. We'll see you on Wednesday for midterm. Thank you.